This student book is the seventh one of a set of student books which altogether provides the complete set of information to master SDMX. It focuses on the data sharing model, the architectures and the mapping process of local data and metadata to SDMX structures. Together with Student Book 8, it describes the SDMX architecture using pull method for data sharing. This student book looks at the data sharing model with the pull and push mode, the data provider architecture using the pull mode, and particularly at the mapping process from non-SDMX data to SDMX compliant data, which will be demonstrated using Eurostat's Mapping Assistant tool. In the context of this session, we speak about the data provider as the organization making the data available. The term data producer is often used as a synonym. On the other side of the data exchange, the data collector can be found, which is the organization pulling or requesting the data for its use. In a data sharing model, organizations agree on a common way to provide access to data according to standard processes, formats, and technologies. SDMX supports different ways of sharing statistical data. In push mode, the data provider initiates the data exchange by sending or pushing the data to the data collector. This can be done by email or dedicated file transfer systems. In pull mode, the data collector initiates the data exchange by fetching or pulling the data from the data provider. The pull method has the advantage of reducing the reporting burden to European and international organizations. In fact, a data reporting organization publishes data only once and let their counterpart pull data and related metadata as required. In push mode, the data provider sends the data to the receiving organization using email or file transfer systems. The received file is then processed in the recipient system, for example, loaded into a database for further processing. In pull mode, the data collector takes the initiative to get the data. When new statistical data is available, the data provider disseminates the data through his database or produces an SDMX ML file containing the data and stores it in a shared place. An RSS feed informs the collecting organizations about the availability of the new statistical data. The RSS feed contains the SDMX query message describing the new dataset, or may contain the URL to the SDMX ML file. Then, the collecting organization chooses the appropriate way to retrieve the statistical data. First option, the collecting organization sends an SDMX query message to the web service. The latter fetches the data from the database and dynamically constructs the SDMX ML file, which is returned back to the collecting organization. Second option, the collecting organization downloads the SDMX ML file directly from the shared place via the URL that is provided in the RSS feed. A data hub is a pull mode based architecture for common data sharing. Data is not previously collected and stored in a central repository, but it is directly accessed from the data provider's databases through a central hub upon request of a data collector. The data collector browses the hub to define the data set of interest via its structural metadata. The hub converts the user's request into an SDMX query message and sends it to a National Statistical Institute's web service. The Statistical Institute's web service converts the SDMX query in a set of SQL queries, fetches the data from the Statistical Institute's database, dynamically constructs the SDMXML file and sends it back to the hub. If the request concerns data of several national statistical institutes, the steps are executed simultaneously for each of them. The hub assembles all the SDMXML files received from the national statistical institutes and presents the result to the user in a readable format. Generally, data are described differently by data providers and by data collectors, who use different concepts and code lists. A typical situation is that, in their databases, data providers' data is already described by local metadata, being not SDMX compliant. The first step to perform is therefore the mapping of statistical concepts and transcoding of code lists of the local structural metadata present in the data provider system against the SDMX data structure described in the data structure definition. The mapping process can be done in several ways, and within the SDMX community different examples can be found. In this session, a simplified mapping process is explained using the Mapping Assistant tool developed by Eurostat. The Mapping Assistant is a desktop application. It supports different storage schemes for the local databases and different database vendors to store the local database and the so-called mapping store. A mapping store database has to be installed locally or on a database server to store the mapping information in a database schema. The main functionalities are the mapping of concepts between local non-SDMX statistical data and SDMX compliant statistical data, transcoding to translate between values of mapped components, and the provision of a constant value for an unmapped component. The mapping store database created by the Mapping Assistant can be accessed by the data retriever module of the SDMX NSI reference service infrastructure to transform the related local non-SDMX data to SDMX structured data. Databases linked to the Mapping Assistant are the Mapping Store, to record and making available the mapping information built with the Mapping Assistant tool, and local non-SDMX databases in different storage schemes that are compatible with the Mapping Assistant. Both may be stored in the same database management system. In this example, Microsoft SQL Server Express with Microsoft SQL Server Management Studio. Now, we have a look at the available storage schemes for the local databases. The storage schemes reflect the type of the physical storage of local data in the local non-SDMX database. The following segments illustrate in a simplified way the storage possibilities which are currently implemented for operation with the Mapping Assistant tool. Scheme A is the most simple one. The SDMX concepts are represented as columns of the local data tables. Thus, there is a direct mapping between local concepts and SDMX concepts. In the storage scheme B, besides the concept mapping, the codes of one SDMX concept are mapped to local concepts. To visualize, the codes of the sex dimension are put as local table columns. This is usually met for a DSD with cross-sectional data representation, where multiple measures are gathered in a measure dimension. In Scheme C, we find local concept codes which represent slave tables. A master table lists these tables where grouped data is stored according to a partial key. This local data configuration can be found for large amounts of data which are grouped with partial keys. For example, country and year are used to group the data into distinct tables. In the storage scheme D, the local data is split into two tables where a one-to-many relation exists. The tables are linked with an ID, the so-called primary key. Beside the distinct schemes, combinations of all the aforementioned storage schemes are also possible. For example, a combination of schemes C and D. In addition to the database storage schemes, PC access files are supported as local data, which can also be mapped to SDMX structures. After launching the Mapping Assistant, a database link has to be selected to create the mapping store with the structure initialized to store all the mappings to be performed. The SDMX structures need to be loaded with the Mapping Assistant SDMX Structure Wizard. In the next step, the local non-SDMX data is linked and the dataset is created, which are the local concepts we intend to map to the SDMX structures. The following census example illustrates the different steps in the mapping process with the Mapping Assistant tool. The steps that can be performed are the following. Step 1. The loading of the SDMX structures, category scheme, data flow, data structure definition, from SDMX ML structure files. Step 2. The loading of the local non-SDMX database schema and the creation of the dataset. Step 3. The mapping of local concepts to SDMX concepts of the data structure definition. And step 4. Transcoding of local codes to SDMX codes of the code lists referenced in the data structure definition. This table shows the SDMX structure of the census data with the SDMX dimensions, measures, and attributes, including the link to the code lists for coded concepts. The loading of the SDMX structure represents step 1 of the mapping process. In the Mapping Assistant, the SDMX structures are shown in overview tables after their loading. Now we perform the dataset creation from the non-SDMX census data. After the connection to the local database with the census data is made, the graphical database query editor is opened. Here, the link between the local data tables is established by the primary key field, which is corresponding to the storage scheme D. Then the columns to be returned have to be specified. Finally, the so-called dataset is saved. The loading of the local database and the creation of the dataset represents step 2 of the mapping process. The mapping and transcoding to be performed with the Mapping Assistant is shown in this overview. This will cover steps 3 and 4 of the mapping process. For example, the local concept age_CMP is mapped to the SDMX concept age. The local concept geo_CMP is mapped to the SDMX concept geo. For the geo and sex code lists, transcoding has to be done between the local codes and the SDMX codes. The codes of the time period concept time need also transcoding. To map the structure of the local dataset to the SDMX DSD structure, a mapping set has to be defined for an existing data flow. This is done in the Tools menu file Mapping Set. The mapping set is put as child of the data flow in the tree on the left side. After selection of the related dataset, the mapping definition can start. In step 3, the mapping links the SDMX concept of the DSD structure to the structure of the dissemination database. First, we map the local dataset concept age_CMP to the SDMX concept age. The required mapping of each of the SDMX concepts to the related local dataset concepts is performed in the following way: marking the components to map on both sides, pressing the plus button to include in the mapping field, press map to effect the mapping. As a result, a line of the mapped components age to age_CMP will be displayed in the performed mappings table. Now, the mapping continues for the other concepts: CAS to CAS_CMP, GEO to GEO_CMP, SEX to SEX_CMP, FREC to FREC, time to time_CMP, and ops_value to ops_value_CMP. Mandatory SDMX concepts with no corresponding local concept can be mapped with constant values. The SDMX concept time_format gets the constant value P1Y for the yearly data format attached. The SDMX concept ops_status is not mandatory, therefore no action is taken. In step 4, we move to transcoding. Transcoding matches values for a mapped concept from a local code list to the SDMX code list. The transcoding rules can be manually defined, provided by a CSV file, or matched by the AutoMatch wizard function of the mapping assistant. For the local concept GEO_CMP and the SDMX concept GEO, the values are represented by different codes. The translation of these codes is available in a CSV text file. To perform the transcoding, we load this CSV file in the transcoding dialog box and save the operation. For the local concept SEX_CMP, we also load a CSV file in the transcoding dialog box and save the operation. To transcode the local time_CMP to the DSD time concept, a dedicated menu is available, where the substring of the code representing the year is highlighted and the related frequency A for annual is selected. At the end, all the mapping information established with the mapping assistant is stored in the tables of the mapping store database. This database can be consulted by any software preparing SDMX data for exchange from local data, provided the SDMX and local data structures remain the same as in the example.